Good afternoon. Hopefully some of us are awake after this rough morning. I know that if I sit down, given that I'm from New York, after 1 minute of sitting down, I do fall asleep, trying to catch up for the time I don't have that at night. But in any case, this was a great introduction to our topic because Eddie was covering Swift on OpenPOWER, which is the proof of concept we have done to measure how to operate or how to the impact of OpenPOWER or Swift running on OpenPOWER. And so I'm Jacob Caspi. I'm a principal architect at AT&T, responsible for our cloud architecture. Tom Mathews is a distinguished engineer with Power System at IBM, and Christian Reis, who's the VP of Hyperscale in Canonical, which we all did this together. So we actually delivered this presentation across the street at the OpenStack Summit. So some of so especially this slide may not be applicable because hopefully everybody here knows what the OpenPOWER is. But what we wanted to emphasize is why we actually looked at OpenPOWER for Swift, given that Swift is not the most CPU intensive or memory intensive application, yet still we feel that it benefited from having OpenPOWER as the base architecture for it for a more efficient use of the CPU. So, Tom, if you can elaborate a little bit more about that.
Right, sure. So, as the chart says, right, I mean, is that there's some characteristics that OpenPOWER has that are really critical for this particular workload, right? It's got a lot of threads, it's got more cache, it's got more bandwidth, and through this POC and some of the performance work that we've done, we still have some performance work to work through, but we see comparatively, fairly significant performance differences, right, in this environment with this workload running on top of OpenPOWER, right? I mean, one of the, at least in my opinion, one of the strengths of OpenPOWER, right, it was built as the workloads that ran on it and so forth, and moving forward, it was built as a data machine, and those characteristics, that were brought forward from that, really have a significant impact on performance in here, right? Because this is, open source. It's just about cost and performance. So we've seen some very good results out of this. The other thing, there's been discussion about accelerators. That's something that we'll be applying to this as well. So.
Keiko, would you like to talk about what is Swift and what we're looking to get out of this?
Sure, Jacob. So as you introduced me, I'm a VP for Hyperscale. I'm a Canonical veteran. In fact, I've been at Canonical for 11 years. And from the very beginning, we've invested in sort of looking at ecosystems and making sure that there is opportunity for multiple vendors to come in and to provide important components. And when you look at the infrastructure layer, we've always understood that it's very important to have multiple architectures. And so I'm going to talk here about Swift and at the end around our tooling, but just to understand, our view is that the tools we provide and the operating system we provide is the same no matter where you're running it. If it's in private cloud or public cloud, if it's on x86, Power, or other architectures, that you've got the same experience, the same tooling, and the application and the operational team as much as possible can navigate regardless of where they are. So our investment in Canonical in general is making easy access to software and to high-value operations. Swift is one of the tools. I'm also responsible for the storage BU at Canonical. So Swift is one of the products that we've looked at for years and said, this is a great alternative for people that are, at the moment, stuck inside expensive arrays or expensive NASs for recording what is typically low IOPS, high volume data that everybody has plenty of and lots of people throw away. So Swift is a great answer for that because it is pure software. It can run on any hardware. In fact, across the cluster, you can have any configuration hardware, and Swift understands the sizes of the machines and how many drives they have and how much storage capacity, and knows how to balance it out. Swift has a two-tier architecture. It has a proxy on the top and object storage nodes at the bottom. The proxy is essentially there to handle API requests, which are of the sort store an object and give you back an ID, or retrieve an object based on that ID. The proxy in Swift is essentially what handles all the northbound communication. Everybody's requesting data or putting data into the object store is talking to it. And the proxy itself streams information, in fact, streams the data back into one or more object storage daemons, which sit in the backend. So the object storage daemons run on the servers that actually have the disks where data gets stored. In this example here, we don't have this on the slide, but we're going to be looking at specifically erasure coding, which is a strategy in which you don't have to replicate all the data. In fact, you can use something which is analogous to RAID inside a single machine, RAID 5 and RAID 6 in particular, where you're calculating parity. And so in Swift, what you do is when you get an object that comes in and you're doing erasure coding, that object gets cut up into chunks. We calculate parity blocks, and those are stored in the underlying object storage targets. The high-level net benefit is that instead of requiring 3 times the copies, which is sort of industry standard for scale-out storage, you may require 2x or 1.8x or less. So it's really a significant savings in terms of disk capacity required. And this is why the investigation's been done here looking at Power as a vehicle for providing erasure-coded back object storage is so important. It's because we really want to see economies of scale and driving down cost in each of the individual components there.
Great, thanks. This was a test environment. Tom, would you mind describing?
Yeah, sure. So this test environment, there were actually 3 Swift clusters here. As part of the work that we're doing, there were 3 Swift clusters here, actually, of the same type. Each one of them had 6 power servers and OpenPOWER servers in them. As a matter of fact, the same ones that I saw in the Canonical pitch a few minutes back. In addition to that, we used 6 Supermicro drawers in the environment, a fair amount of storage here, and also a dedicated proxy server in the environment, and 10 gig networks for data and 1 gig for management in the environment. And the software was Ubuntu software, obviously, Swift and OpenStack, right? Coming out of the community.
So we've had 2 goals when we started this proof of concept. The first is strict functionality, meaning does Swift work on OpenPOWER in the same way that it works on x86, meaning from a functionality perspective. Are we losing anything? Does it take a lot more effort to deploy? Did we get any gotchas while we did the installation? And the response to that is pretty much it went as well as we expected to have gone if we have gone to any new x86 environment. So from a Swift deployment perspective, we found very little differences on whether we went to an OpenPOWER processor versus x86 processor, which is very important for us at AT&T because we are very concerned with large-scale operations and making sure that operation teams have unified tool and unified deployment, that we don't have to differentiate between one CPU versus the other, which would have caused a barrier to entry within AT&T. The other thing that we were testing is, of course, performance, meaning how well does the cluster perform, and what kind of efficiency are we seeing versus x86? Of course, we did not have a benchmark. We did one-to-one comparison between x86, but as Keiko mentioned, we're testing erasure coding. In this case, it's 2 data and 2 parity, which allowed us to do a 1 to 1.5 data replication. So imagine that's, it was more or less half the amount of hardware that we would have needed if we have done it with standard 3x replication, which is normal with OpenStack, with OpenStack Swift. As you can imagine, AT&T has huge amount of data, and every ounce we can squeeze out of the hardware, and every ounce we can make more efficient in terms of storage, translate to a huge savings over the scale of data that we store. And that's one of the major reasons that we looked at OpenPOWER, because if we can do the same workload with, let's say, less CPUs, less power, less space, when you do look at exabytes worth of storage, that translates to a fairly significant amount of reduction in capital investment. So some of the test results, basically, we've done various loads, anything from 900 objects as a small load to 2,000 objects as the high load, and varying the amount of workers on the servers. And as you can see from the graph, we barely touched 50% utilization on those servers. Now, of course, we went with the servers that we had in the lab. We didn't do much optimization, but as you can see, we definitely over-provisioned the servers. So even if we cut the CPUs by half, we could have still managed to do the same amount of workload that these servers produced. And the other thing that we measured is the failure rate, looking at 64K objects to 512K objects, given that we have variety of workloads on these. You can see from a success ratio rate, meaning how many times that did we have to go back and retrieve the same data, there was almost no significant discernible difference between when we loaded with 32 workers or 1,100 workers. And pretty much we've concluded that, at least with our environment, we could not generate enough load to stress the environment and overload the servers. Now, the other thing that is very portable is repeatable. Is a very repeatable solution and repeatable deployment. Of course, when you do, again, exabytes worth of data storage, you must have really good tools. You must have automated deployment. So that's where some of the tools from Canonical make a difference.
Yeah, and in fact, object storage in particular is a great example for OpenPOWER coming in easily into any data center. Everyone needs an object store. Currently, people are putting data into S3 in buckets, paying $30 per terabyte per month. And so if you look at that, there's obviously an opportunity to come in. Power can come in without changing any of the operational tooling because we're using exactly the same operating system and tools on top here as in anything else that they would already be using there. Benchmarks are hard, so we normally tell people they have to be reproducible, and we've worked together with AT&T and IBM to make the entire set here reproducible. We provide automation tooling with Maz and Juju, which again are what we use at every single OpenStack and storage customer that we have. And so the code in there is code which understands how to handle quirks and networking peculiarities across every customer that we've ever worked with. We invite you to come and talk to us more about what it is that we did to get the reproducibility scripts on your own and to understand how Power and Swift together can make a difference. Thanks very much.
Thank you. And I really like to thank IBM and the Austin lab team for helping us set up this environment. I know they had to work and crunch time to give us these results so we can present in this forum. And of course, my team, especially Cindy Bilovitz and my team, for working nights and getting this result in time. Thank you.